So we have to think about, you know, if electrons are being pulled, and that's correct, electrons get pulled through a wire here, but what is going to pull the electrons? Well, something obviously that likes electrons. So what likes electrons? Oxidizers. So we want an oxidizer to pull the electrons through. And can somebody think about what pulls the electrons? Is it the zinc metal that pulls the electrons through? Could be. Could be. Does the reducing agent pull electrons, you say? Do reducing agents take electrons? No. What takes or pulls the electrons is the oxidizing agents. So the oxidizing agent is where we're going to end up consuming the electrons, and the reducing agent is going to be zinc. So this setup looks good, except the electrons are just going the opposite way. The electron should go to the copper 2. We need copper 2 ions. The copper 2, not the copper metal. The copper 2 wants to oxidize something. Yeah, and so we need to feed the electrons to copper 2, but we don't want the copper 2 to eat up. Well, in other words, we don't want copper 2 to eat the material. We just want copper 2 to eat the electrons. So what we need is we need some kind of electrical conductor that won't be attacked by copper 2. So zinc metal, a good metal to use here. Zinc metal is not a good metal to use because copper 2 will attack the zinc. However, if we make this out of copper metal, then we're good. Because will copper 2 eat up copper? No, they're equal. So they're equal. And so the electrons are going to be fed to the copper 2 here. And so what's pulling the electrons? The copper 2. But where are the electrons coming from? The electrons are coming from the Now, the situation here is you want to give this some thought. This battery stuff's not easy, and the thing is, it's a struggle to get all the jargon down. It's a struggle to understand how conceptually they work. You know, it's a struggle. It's not easy. I don't think I've ever met somebody who found it easy. You know, and so what you want to do is you want to at least initiate that struggle. That is, to try to figure out how this thing works. And so, I mean, I can tell you, but if it doesn't come from your own, it's like the definition. The definition of Le Chatelier's doesn't come from your own words, and it's not very memorable. And so here, we're going to have zinc over here, and the zinc is what's going to give up the 2 electrons. So zinc solid goes to Zn2 plus 2 electrons. And so we have to have liquid over here. What's a liquid we got to put in here? All we're going to put in here is water. That's all we need is water. Why do we need water? We need water to help stabilize the Zn2+, because what's going to happen here is the zinc is going to go to Zn2+. Well, Zn2+ is more stable in water than it is in air. Zn2+ is more stable in water because the water molecules can surround the zinc 2+ and encapsulate it. Do you know what that's called when water surrounds and encapsulates ions? when water surrounds and encapsulates ions, so this is, we need water to help stabilize this, because if we were to generate zinc ions in air, it'd be highly unstable. At least zinc ions, this is copper too, but zinc is a 2+ also. So imagine this as being Zn2+, and it's surrounded by these water molecules which help stabilize the charge. The negative oxygens point to the positive. You know, these are partial negatives, so this is not a full negative charge, but what's this called? This one is called Nobody know? Hydration or solvation. And so these ions have been hydrated or solvated, and we call that. And so we got to have hydrated ions, otherwise they're going to be unstable. But even with hydrated ions, it's still unstable. It's terribly unstable because we have hydrated cations here, but we also need, what else? If we have cations, we also need anions. So if you were to go and try to buy a bottle of zinc ions, let's say you're on a low sodium diet. If you're on a low sodium diet and you went to buy table salt and you said, I want the table salt without the sodium, can you get it? No, I mean, it's crazy because you can't just get chloride. Well, probably chloride doesn't taste very good anyway, but you can't just get the chloride. And the same thing here, we got the Zn2+, but that's going to be, even though we're going to have hydrated ions, which helps it, it's still terribly unstable because there are no anions. There are no anions in here. There are no anions in here. This battery is not going to last very long. In fact, it's going to shut down. The battery is going to shut down because if you just generate cations here, you're going to generate so much static electricity, it stops everything. You can't generate too much static electricity. And so in order to help stabilize it, one, we have hydrated ions, and two, we need anions. Where are the anions going to come from? So you had it right here. It's the potassium sulfate. The potassium sulfate, we need this sulfate ions to go this way. And so the sulfate ions are going to, the anions are going to go this way to help stabilize that charge. So we'll have both hydrated cations and hydrated anions. And the charges should balance overall. Over here, what's happening? Over here, the copper 2 is being fed electrons. It's being fed electrons by the copper metal. The copper metal we call an electrode. And it's the electrode's job to transport the electrons. So this electrode is going to feed the electrons to copper, and that copper is going to deposit as a solid. And so what's going to happen here is this electrode is going to be eaten away. This electrode here is just going to get thicker and thicker because what's going to result is the copper 2+ comes in here, takes up 2 electrons, and deposits copper solid. And that copper solid is going to build a precipitate on top of this electrode here. This is also an electrode because this electrode feeds the electrons. So the electrons are going to be generated down here, and the electrons are going to travel through the electrode into the wire. This is just a piece of copper wire. And the electrons travel left to right. This is by convention. The electrons can go any way it wants, up and down, or down and up, left to right to left. It doesn't matter. Electrons are just going to go to where they're being pulled. But when we do the drawing, we usually do it like this. We like to go electrons left to right. And even though this is also an electrode, we have a specialized name for this electrode. What is the name for this electrode? You know, we got 2 electrodes, but they're doing different things. We call this electrode the anode. This is the anode. It's the anode. Where did that name come from? The anions. The anions go to this electrode. So if the anions go to that electrode, it's called the anode. Whereas for every copper 2 that's lost, there's 2 nitrates that are alone. And those two nitrates that are alone aren't going to be happy. And so for every copper 2 that's lost, 2 potassiums have to come in to take the place of the lost copper 2. And those 2 potassiums will keep the nitrates electrically neutral. Even though these are hydrated ions, and these will be hydrated ions, we need to maintain electrical neutrality. And so this electrode is called the cathode. So this is what I said last time. I said it's alphabetical. A to C, anode to cathode. Electrons go left to right. Anions go to the anode, cations go to the cathode. And so this is how it operates. Copper 2 is going to be pulling on the electrons. Is zinc going to be pushing the electrons through? Electrons get pushed through? No. Copper is going to pull. Zinc is going to resist. How hard is it going to pull? Well, what we can do is we can hook up a voltmeter and tell how hard it pulls. The higher the volts, the more pull on the electrons here. And this voltmeter is going to read 1.1 volts. That's solved. And the volts is like pressure, you know. Although water pressure, you know, if you try to cap this, you can feel the water pressure. The water pressure is being pushed through the pipe. Here, the electrons are being pulled through the pipe being copper, in this case, the copper wire. All right, so at the anode, electrons are being generated, and we have oxidation and reduction occur. At the anode, oxidation occurs, and this is our reducing agent. At the cathode, reduction occurs, and this is our oxidizing agent. What charge do you think the anode is, negative or positive? Well, actually, since it's generating electrons, it gets negative, and since this is pulling electrons, the cathode gets the positive. The electrons are being pulled into the cathode. They're being pulled into the cathode by the oxidizing agent. And so the net reaction for this is Zn solid plus copper 2 plus yields Zn2 plus copper solid. Is there a driving force for this? Yeah. This is a reducing agent. This is a reducing agent. So we're going from a stronger reducing agent to a weaker reducing agent. This is a stronger oxidizing agent to a weaker oxidizing agent. This is the qualitative driving force. The quantitative driving force we do in voltage for redox reactions. We do it in volts. You know, how strongly are the electrons being pulled through the wire of the circuit. All right, so this is the sketch of the voltaic cell and its basic operations. So just some review on that. Now, that was the figure. This is right at the beginning of chapter 19. So figure 19.1, chapter 19. And so we see this is typical anodes written on the left, cathodes written on the right, electrons go left to right. That's the salt bridge. It's pulling the electrons through. This electrode is growing thicker, this electrode is being eaten away. Oxidation happens at the anode, reduction happens at the cathode. So this is the basic cell operation. If instead of putting a light bulb there, we put a voltmeter, then we can measure how strong that driving force is. If we put a voltmeter there, we measure 1.1 volts. 1.1 volts. All right, so that's the review of the first part of chapter 19. The second part of chapter 19 does the, well actually, we also talked about electrolytic cells. A voltaic cell is a battery. The electrolytic cell, did I talk about this already? An electrolytic cell, what we do is we force the electrons to go backwards. And so one thing we can do is recharge this battery. Once this battery goes dead, what's the voltage? When this battery goes completely dead, the voltage goes to 0 volts. The electrons aren't being pulled through the battery anymore. And so one thing we could do is we could recharge the battery. You know how we recharge the battery? We force the electrons to go backwards. How do you force electrons to go backwards? You put a power source or a bigger battery in here. And so what they're showing is they put a bigger battery in here, and they're going to use that bigger battery to push the electrons the opposite direction. And so if we push the electrons the opposite direction, that's going to reverse this. And so what's going to happen is that the copper metal will be oxidized to copper 2, generating electrons, and those electrons will be fed to the zinc 2+, which will be reduced to Zn metal. And so it's just going to reverse this reaction. So we put a power supply in here, force electrons to go backwards. Electrons go backwards, we recharge the battery. Okay, that's one application of this, the electrolytic cell. The other application of the electrolytic cell is to generate high energy chemicals. Here's an example of a high energy chemical, chlorine gas. Is chlorine gas very stable compared to chloride? Well, I'll eat chloride in table salt, no problem, but would I eat chlorine gas? No. Or inhale chlorine gas? No, because why? It's a high energy, highly reactive chemical. So where does chlorine come from? Chlorine's man-made, or maybe it's in the volcano, but it's unstable. So how do you make this unstable? Well, you force the electrons off here. How do you pluck electrons off chloride? Chloride's very stable. How strong of a reducing agent is chloride? Chloride's one of the worst reducing agents. If you think, what is the worst reducing agent you can think of? Fluoride. Fluoride would be the worst reducing agent. And what would be the, oops, this was not what I wanted to, okay, that's something else. Okay. What was the other one? The worst one is fluoride. This is what I want to get to. The worst one is fluoride here. But you can see chloride is pretty bad too. And so that means chloride is pretty stable. However, chlorine is not stable. Chlorine is a very powerful oxidizer, you can see here. And so, let's go back to this. The electrolytic cell. So one way we could generate this highly reactive oxidizer is by electrolysis. So if you take chloride, strip its electron. How do you strip an electron? You turn up the voltage. You turn up the voltage high enough, then that means there's going to be a strong pull. Take a look at the positive terminal of the battery. The positive terminal is trying to suck in electrons. If that's a high enough voltage, if it's positive enough, it can strip the electrons off chloride. Now, is it easy to strip electrons off chloride? No, it's not. But put a big enough battery there, like an Acme battery like that, and it's going to strip off the electrons. Now, over here, are sodium ions, are those good oxidizing agents? Are sodium ions good oxidizers? What's the worst oxidizer you can think of? The worst oxidizer you can think of is probably lithium plus. Lithium plus is at the bottom. That's the worst oxidizer, right? And then where's sodium ion? It's one of the worst. Sodium ion is one of the worst. Sodium ion can't oxidize anything. Well, sodium ion can't oxidize anything, but you can force it, you know, to take the electrons. How do you force it to take the electrons? Well, you put enough force on the electrons. Voltage is also called electromotive force. It's force on the electrons here. And so if you have a high enough EMF, electromotive force, or if you have a high enough voltage, you can force sodium ions to take the electron. When sodium ions take the electron, it forms sodium metal. And so what we can generate here is we can generate sodium metal and chlorine gas, two highly reactive chemicals. This is a powerful reducer, that's a powerful oxidizer. You need a barrier to separate these two. If there's no barrier here, you're going to get an explosion. The sodium and chlorine react explosively together. And so that's electrolysis. You're forcing the electrons to either recharge a battery, or you're forcing electrons to generate highly reactive chemicals, chemicals that normally wouldn't form. Now you can't have any water around because sodium is very reactive with water, so this is molten sodium chloride, or in other words, liquid. This is not aqueous sodium chloride. This would never work in aqueous sodium chloride to generate sodium metal. Instead, you generate oxygen gas, or hydrogen gas. Sorry, hydrogen gas. And so here's just showing the electrolysis of sodium chloride here, using an external power supply or battery. All right, this oxidation numbers, you guys are you guys comfortable with oxidation numbers now? Oxidation states? So I'm going to skip this. We already did it. You're comfortable with oxidation reduction, oil rig? All right, so let's try an example here. Determine the element oxidized and the element reduced in the lead storage battery. So this is like a car battery here. What is oxidized? Well, oxidized, oil rig, oxidation is lost. So which atom loses electrons? You tell? Which atom loses electrons? Well, over here we have sulfate. Over here, is that sulfate? Yes. And so sulfate doesn't change. It's here and then it's here. Although it precipitates, it's still sulfate. And so in other words, what's oxygen? What's the charge on oxygen, or the oxidation number or oxidation state on oxygen? Oxygen is normally -2. And that means sulfur is plus 6. And the same thing over here. This is lead 2, so oxygen is -2. This is -8 plus 6. -8 plus 6 is -2, and this is +2. And so sulfur stayed at +6, oxygen stayed at -2, so there's no change. It didn't gain, it didn't lose electrons. But something else did. Let's take these one at a time. This is lead. What's the charge on lead? 0. It's the element. Okay, then we go to the product. What's the charge on lead here? +2. So this lead must have lost 2 electrons.